All right, guys, so what we're going to be looking at here is the very last idea from first trimester, where we're going to kind of tie a lot of the things that we've talked about in this class together. Well, this is a topic that is known as related rates. This video will probably be broken into two different parts just because this is kind of lengthy, and I want to make sure that we understand it well. So here we go. We'll start into related rates. If you remember when we had x plus xy plus y squared equals x to the third, and we were using implicit differentiation to take the derivative, what we found was anytime you took the derivative of a y, you put a dy dx after it. And that dy dx, what that stood for is that meant that y was some sort of function that had x in it. We didn't know what that function was, but we knew the process that we would use to take the derivative of something with a y. So we just said dy dx represents the derivative of y with respect to x. Okay? It was still a small change in y over a small change in x. It just represented something slightly different because we didn't know what y actually stood for. Okay? So if we had if we looked at this formula, volume equals 4/3 pi r cubed. This is for the volume of a sphere. If I wanted to find dV dr, we could see pretty easily that that's 4 pi r squared. And the dV dr, what that stands for is a small change in volume divided by a small change in radius. If this were being measured in like cubic feet per feet, then it would be like cubic, that's exactly what you would say, is I'd be measuring that in cubic feet per feet, which doesn't make a ton of sense. Like, why in the world would I care about a rate that is cubic feet over feet? That just, you wouldn't use that in any real life scenario that I can think of anyway. So, although the formula is very useful to help us find the volume, if I find dV dr, then that really doesn't stand for anything that I am going to be using, especially when it comes to a derivative. Okay? And again, that's kind of confusing because we're talking about a rate of change. It's an instantaneous rate of change because that's what the derivative stands for, but it is still a rate of change. If I say I'm changing in cubic feet per foot, most people would be like, I don't really get what you're talking about. Okay? And so the problem is, in real life scenarios, formulas like volumes or areas can be used a lot if we realize that there might be something else going on other than what we were looking at there. So as a different side note, kind of what I want to say is, let's say we were looking at this function. Now this is a position function, s equals 4t squared plus 2t minus 1. If I were to take the derivative of this position function, I would get ds dt is equal to 8t plus 2. Or some of you might remember ds dt as a velocity formula, where I'm saying my velocity is equal to 8t plus 2. And if s were measured in feet and time was measured in like seconds, then I would say that my velocity would be in feet per second. Or maybe it's miles per minute or meters per hour. All of those are measurements that actually make sense when we think about them logically. Like if I say this is a formula in miles per hour that tells you how fast you're going, nobody's going to question and say, what in the world is miles per hour? Again, they might say it over here with like cubic feet per foot, but not miles per hour. And the key to understanding these is story problems, when we use the derivative, because we are talking about a rate of change, they make a lot of sense as long as you're taking the derivative of something with time in it. Time makes sense. Like when I look at like dV dt, that's a change in volume divided by change in time. So like cubic feet per second. Or ds dt, meters per minute, something like that. Those make sense because we can make sense of that because that is how rates are measured. It's always something divided by a change in time, like a unit of time. The problem is, again, it's very difficult to write an equation that tells us how fast something is going at any given time, or how fast an area is moving or changing, or what the area is at any given time. Although an area formula for like a circle is very simple, trying to find a function that relates it to time would be very difficult. And you'll notice this equation right here, like we looked at it once already. Or Pythagorean theorem, a squared plus b squared equals c squared. A very useful formula, but unfortunately for us, it's not a formula that we can use to actually find the derivative of, or find a rate at how fast something's going because there's no time in those equations. So what we do here in these problems is we say, okay, if time's not in them, I need to force time into the equation somehow. And so, as you see down here, we've got area equals pi r squared. And here's how we're going to kind of force the time into the equation. If I were to look at area, I would say that area is a formula that, even though we don't know what it is, I'm going to say area is equal to something with time in it. Maybe it's equal to time squared plus e to the t. I don't know. But I'm going to say that area is a function of time. Then I'm going to do the exact same thing for the radius. The radius, I can tell the radius at some given time based on the length. Again, I don't know what the formula is, but in reality, what I'm going to do is I'm going to force that to be a function of time. So I've got a of t equals pi times r of t, and all of a sudden this problem takes on a much different meaning. And we'll talk about what that is in the second video, because this is more of a setup for how do we get ready to use these related rates questions. So if you have any questions so far, please let me know. Otherwise, watch the second video where we can see how this is applied.